Imagine you're standing outside a mysterious closed room, and you can ask for anything you desire. The moment you open the door, you'll find that exact thing inside. For example, you could ask for something simple like an apple or something extravagant like a brand new Mercedes. You could even wish for something fantastical like a unicorn. Before you make your choice though, every possibility exists within that room. It could contain an apple, a car, a unicorn, or an infinite number of other things. But the moment you decide and open the door, all those endless possibilities disappear, leaving only the one thing you asked for. In a way, the act of choosing collapses the infinite potential into a single definite reality. You might be thinking this all sounds like pure fantasy, but surprisingly, according to quantum mechanics, it's not just imagination. It's how reality actually works at the microscopic level. However, many scientists have challenged this idea, and there is no clear explanation for why reality collapses. Some believe that observation or measurement forces reality to take a definite form, but Albert Einstein didn't agree with this and argued that reality should exist independently of an observer. The Schrödinger's cat experiment highlighted this problem, showing how the idea of observation creating reality leads to strange paradoxes. This debate raised even more questions about the nature of reality, and for a long time, no one could fully explain how reality unfolds. But wait, a recent experiment in quantum mechanics has shocked scientists. Previously, in all quantum experiments, the observer was considered a fixed entity separate from the system being observed. But a new study has revealed something incredible: the observer itself can also exist in a superposition of states, just like the particle it is observing. This new idea is called the quantum reference frame theory. When scientists reanalyzed previous quantum experiments using this new approach, they discovered that reality is even weirder than we ever imagined. This breakthrough might finally help solve some of the biggest paradoxes about reality. To understand this better, let's explore this new theory in depth and see how it shocks scientists by revealing some bizarre and unexpected nature of reality. Inside every atom, the tiny particles that make up our world don't behave the way we expect from everyday experience. Scientists have spent decades studying electrons, and they've discovered something astonishing: an electron doesn't have a fixed position like a planet orbiting a star. Instead, it exists in a cloud of possibilities, meaning it could be anywhere around the nucleus at any given moment. But here's where it gets even stranger: the moment you try to observe or measure the electron's position, all those possibilities disappear, and the electron chooses a single location. This is exactly like the magical room before you open the door. Every possibility exists, but the act of observing forces the room, or in this case, the electron, to settle into just one outcome. It suggests that reality, at its most fundamental level, isn't set in stone, it's shaped by observation and interaction. When Einstein learned about this strange nature of the quantum world, he was stunned. Einstein was skeptical about quantum theory, especially its idea that events at the smallest scales are governed by probability rather than certainty. He famously said, "God does not play dice," expressing his belief that the universe should follow clear deterministic rules rather than randomness. In other words, he thought that if we fully understood the laws of physics, we should be able to predict every event precisely without relying on chance. However, modern physics has shown that quantum mechanics is fundamentally probabilistic, meaning that at a microscopic level, nature does involve randomness, and we can only predict the likelihood of events rather than their exact outcomes. To challenge quantum mechanics, Einstein pointed out several paradoxes, situations where the predictions of the theory seem to contradict common sense or fundamental principles of physics. One of the most famous paradoxes he revealed was the EPR paradox, named after a 1935 paper he co-wrote with physicists Boris Podolsky and Nathan Rosen. In the EPR paper, Einstein and his colleagues revealed a strange phenomenon called entanglement. When two particles become entangled, their properties remain connected no matter how far apart they are. If you measure one particle, the other particle's state seems to be instantly determined, even if they are light years away from each other. Einstein found this deeply troubling. He argued that this kind of instant connection violated the principle that no information can travel faster than the speed of light, as stated in his theory of relativity. Einstein and his colleagues argued that if quantum mechanics was correct, then either information is somehow traveling faster than light, which would break the laws of physics, or the particles must have hidden information that predetermined their states before they are measured. Einstein favored the second explanation because he believed that physics should be deterministic, meaning that everything should have a definite cause and outcome. He thought that quantum mechanics was incomplete and that a deeper theory, one that included these hidden variables, would eventually explain reality in a more logical and predictable way. For many years, physicists debated whether Einstein was correct in thinking that quantum mechanics was incomplete. However, in the 1960s, physicist John Bell proposed Bell's theorem, which provided a way to test whether hidden variables could explain quantum mechanics. Later experiments, particularly in the 1980s and beyond, confirmed that Einstein was mistaken. Quantum entanglement is real, and no hidden variables can fully account for its effects. Also, the Copenhagen interpretation says that before we observe a quantum particle, it doesn't have a fixed state. Instead, it exists in superposition, meaning it is in all possible states at once. But when we measure it, this uncertainty disappears, and the particle instantly settles into one definite state. This process is called wave function collapse. In simple terms, this means that our act of observing or measuring something actually shapes the reality we see. Even though Einstein was eventually proven wrong, he strongly disagreed with the Copenhagen interpretation, especially the idea that reality depends on observation. He argued that it was too strange and incomplete to say that something only becomes real when we measure it. Interestingly, around the same time, another famous physicist, Erwin Schrödinger, also found this idea unsettling. To highlight its problems, he came up with a famous thought experiment called Schrödinger's cat, which imagined a cat inside a box that could be both alive and dead at the same time until someone looked inside. Imagine a cat is placed inside a box with a radioactive atom, a Geiger counter which detects radiation, a poison bottle, and a hammer. If the radioactive atom decays, the Geiger counter detects it, triggering the hammer. To break the poison bottle which kills the cat, and if the atom does not decay, the cat remains alive. According to the Copenhagen interpretation, the radioactive atom is in a superposition, it is both decayed and not decayed until measured, and the cat should also be in a superposition of both alive and dead at the same time until someone opens the box and observes it. But physicist Erwin Schrödinger raised an important question, like, what counts as an observer? Does the cat itself observe the atom's decay? If the cat can already observe the event, then the wave function collapse happens before a human looks, making superposition meaningless in this case, and the cat is either alive or dead before we look. Or does wave function collapse only happen when a human opens the box? If that's true, then the cat really is both alive and dead at the same time, which doesn't make sense in our everyday experience. Einstein was deeply impressed by Schrödinger's thought experiment and even wrote him a letter in which he expressed his thoughts on it, saying, "You are the only contemporary physicist besides Laue who sees that one cannot get around the assumption of reality if only one is honest. Most of them simply do not see what sort of risky game they are playing with reality. Reality is something independent of what is experimentally established. Nobody really doubts that the presence or absence of the cat is something independent of the act of observation." Schrödinger's famous thought experiment with the cat actually supports Einstein's skepticism about the role of an observer in quantum mechanics. Einstein questioned whether reality truly depends on an observer or a measurement to exist. Even today, scientists are still trying to understand what actually causes the wave function to collapse. The mystery remains unsolved, and some of the greatest minds in physics continue to debate it. Even Nobel Prize-winning physicist Dr. Roger Penrose believes that conscious observation or simple measurement does not cause the wave function to collapse. What collapses the wave function is physics, so there is something in physics which collapses the wave function. Schrödinger's equation and quantum theory as a whole are wrong. It's not Einstein was wrong, quantum mechanics is wrong. Now I say this very blatantly because it's a blazing topic. I mean, Einstein and Schrödinger were much more polite, they said it's just incomplete. Well, over the years, scientists have proposed several other theories to explain the superposition of particles and the collapse of those states. One of the most famous interpretations is the many worlds interpretation. It is slightly different from the Copenhagen interpretation. In Copenhagen, the cat is in superposition until an observer opens the box, and the moment an observer looks inside, the act of measurement forces reality to settle into a single definite outcome. But in the many worlds interpretation, when the box is opened, the universe splits into two. In one branch, the observer sees the cat alive, in another branch, the observer sees the cat dead. Here, the wave function never collapses. Instead of choosing one reality, the universe splits into multiple parallel realities, with each possible outcome happening in its own branch. According to this interpretation, the observer is not special. They also split into multiple versions along with the universe. Some other interpretations revealed that two different observers see different realities and that there is no such thing as objective reality. Back in 1961, Nobel Prize-winning physicist Eugene Wigner outlined a thought experiment that demonstrated how the strange nature of a universe allows two observers to experience different realities. In other words, according to our best theory of the building blocks of nature itself, facts can actually be subjective. If facts can be subjective at the quantum level, then reality itself might not be an absolute fixed entity. Instead, it could depend on the observer's perspective and their relationship to the system they are measuring. At first, this might seem bizarre. After all, in our everyday world, facts appear fixed, a tree exists whether or not someone looks at it. Each of these interpretations tries to explain the strange nature of reality, but they also have weaknesses that prevent them from being universally accepted. Like the Copenhagen interpretation, which says that reality is objective but depends on the observer, it does not clearly explain what counts as the observer or why observation causes wave function collapse. The many worlds interpretation argues that all possible realities exist simultaneously, and each choice or observation creates a new branching universe, but if all possible outcomes happen in separate universes, why do we still follow probability rules in quantum mechanics? Some other interpretations suggest that reality is not objective at all. Instead, reality is different for each observer, meaning that what is real depends on the perspective of the observer rather than a single absolute truth. But if reality is different for each observer, then how do observers agree on objective facts? After exploring these theories and paradoxes, we are left with some fundamental questions that still have no clear answers. Well, tighten your seatbelt, because in a recent study, scientists uncovered a new understanding of the quantum world, revealing something so strange about reality that will shake your foundations. A groundbreaking experiment suggests that even the reference frames of observers, the perspectives from which they view quantum events, can exist in a state of superposition. This means that an observer's position may not be definite, but could be spread across multiple possibilities. The findings have major consequences for our understanding of reality. In the Schrödinger's cat experiment, it's not just the cat that exists in a superposition of being both alive and dead. The observer can also be in multiple superposed states. Before diving into the quantum world, let's understand a simple concept, a reference frame. Imagine you are sitting in a moving train. If you look at someone sitting next to you, they appear still, but to an observer standing outside, both of you are moving at the train's speed. This difference in perspective is because of reference frames, different points of view from which motion and positions are measured. In classical physics, reference frames are straightforward. A moving car has its own reference frame, and a person standing on the road has a different reference frame. But in quantum mechanics, reference frames become weird because objects can exist in superposition, meaning they can be in two places at the same time. To understand this, imagine two observers, A and B, each using a different reference point to describe the world. Normally, we think of one observer as stationary and the other moving, but in the quantum world, things get weird. Suppose A is attached to a tiny quantum object that has a probability of being in multiple places at once. Another observer, B, is a separate observer watching A. According to quantum reference frame theory, from the perspective of another observer, B, the observer A is not at a single definite position but is spread out in a quantum superposition, just like the particle. So if observer A performs a measurement, their result might not match what observer B sees, because B sees A in a superposition. Surprisingly, from A's perspective, it is B who appears to be in superposition. This means that superposition is not an absolute property, it is relative. What looks like superposition from one observer's reference frame may not look the same from another's. Well, it resolves some of the major paradoxes in quantum mechanics, such as when Schrödinger questioned the idea of superposition by asking, does the cat inside the box already know whether the radioactive decay happened? If the cat can observe its own fate, then from the cat's perspective, there is no superposition, it either lives or dies based on the decay. No previous interpretation of quantum mechanics fully answered this question, but according to quantum reference frame theory, the cat inside the box does not have a fixed reality either. From the cat's point of view, the observer outside the box is in a superposition of two states, one where they see a dead cat and one where they see a living cat. This means that superposition is not just about the cat, it also applies to the observer, depending on the perspective taken. Instead of having a single objective reality, quantum reference frame theory suggests that reality shifts depending on who is observing and from where. This changes our entire understanding of what it means for something to be real. Now, let's make things even stranger. What if B is also anchored to a quantum object that's in a superposition of two locations? Then A's quantum state is now smeared out in two different ways, depending on the possible locations of B. Because determining B's quantum state determines A's state, here we can say that A and B are now entangled. This reveals that even entanglement is relative. The properties of quantum systems are not absolute but depend on who is measuring and from which frame of reference. This challenges our classical idea that entanglement is a fixed, absolute relationship between two particles. Instead, entanglement is itself observer-dependent. Quantum reference frame theory changes how we think about reality by suggesting that even the observer is in a superposition. It says that what we see as reality depends on our own quantum state. This means that two different observers in different quantum states might experience different versions of reality. Unlike the Copenhagen interpretation, which says reality is objective but depends on measurement, or the many worlds interpretation, which says all possible realities exist in parallel, quantum reference frame theory suggests that there is no single absolute reality, only different perspectives based on the observer's quantum state. This idea also solved major paradoxes in quantum mechanics. If the cat is in superposition and the observer is also in superposition, then from the cat's point of view, the observer is in multiple states as well. This removes the need for wave function collapse, which is one of the biggest mysteries in quantum mechanics. Instead of collapsing, reality just shifts depending on the observer's quantum state. This theory could even help bridge the gap between quantum mechanics and relativity, offering a new way to understand spacetime and the very nature of existence. If this new theory is correct, then reality itself is not fixed, it's a web of interacting quantum perspectives, constantly shifting depending on the observer. Well, that's the end of this video. If you found it interesting and informative, let us know your thoughts in the comments, we'd love to hear from you. Also, if you'd like to support our work, you can do so by purchasing our t-shirts or donating via Super Thanks. Your support helps us create more amazing content. Thank you for watching.